Hi, good morning. It is Tuesday, March 31st. And if you would, please take out your books. I'm going to start by going over the questions on pages 147 and 148 that I had asked you to do yesterday. Starting with 147, it says, which factors must be equal uh, when a reversible chemical process reaches equilibrium? This question comes up in two different forms. In terms of asking about what's happening at equilibrium, it's either asking about rates or concentrations. Rates are equal at equilibrium. That's what's equal. Quite often they ask about concentrations. Concentrations are constant. That's what makes the rates equal or allows us to determine that the rates are equal. So if your product and reactants are remaining constant in their amounts, remember the curves that I showed you? That's where the curves go up and go flat or go down and go flat. The concentrations are remaining constant. That means the reaction forward and the reaction reverse must be at equal rates. So the answer to number 18 would be 2. And that would cause the answer to 19 to be 2 also. 19 asked about the concentration of each reactant and each product. They're going to be constant at equilibrium. Okay. Number 20, an open flask is half filled with water. The water is going to evaporate, indicating only forward reaction. What will allow it to reach equilibrium? Well, it says add more water, decrease the temperature, increase the temperature. Those things would only change either the forward or the reverse reaction. What's going to allow it to come to equilibrium is stopping the flask. If you stop the flask, the molecules can't leave. They'll have to return to the liquid state. Question number 1 deals with saturated solutions. Solution equilibrium always exists. I don't like the word always being there, and I'll explain why afterwards. Solution equilibrium always exists in a solution that is too saturated. I want to add to that note, there should be some undissolved, so it can go from dissolved to undissolved, dissolved to undissolved. That would be a saturated solution, but it doesn't really stipulate that in the question, so I don't like the fact that it didn't say that. Number 22, given a hypothetical reaction, A plus B yields C and D, or in equilibrium with C and D as we have the double arrow. The answer is going to be 3. Rate of the forward and reverse reactions are equal. 23, remembering our reaction diagrams. What does the catalyst do? The catalyst lowers the hill. So if the hill is lowered, the heat of reaction, potential energy of the products, potential energy of the reactants, those do not change. Okay? So the answer is 4. Rates are going to increase, of course. Catalyst lowers the hill for the forward and the reverse, right? There's only one hill. So it lowers the hill, so the forward is faster, the reverse is faster, and obviously the activation energy is lower because the hill is lower, but it does not change the heat of reaction. 24, for reaction at equilibrium, which change will increase rates? Catalyst would. It's not a choice. Temperature will. Temperature will increase the rate of both the forward and reverse. It'll increase the rate of an exothermic not so much. It'll increase the rate of an endothermic even more. I'll give you an example. Melting of ice. When you heat ice, it melts faster. That doesn't mean that the reverse reaction won't increase, but the forward reaction increases more. Both will increase. Temperature increases the rate of every reaction. Next page, 25. Okay. In a reversible chemical reaction, chemical equilibrium is obtained, okay, for when the concentrations remain constant. 26 just asks us to determine what an increase in temperature is. This was more for our matter and energy topic, but the answer is 1. 255K to 273K. Remember, they give you the Celsius temperature. You have to convert it to Kelvin so you can make equal comparisons. 0 Celsius is 273 Kelvin. Number 27, which describes this reaction at equilibrium. Rates are equal, right? So the rate of the forward, rate of the reverse, they're not increasing, not decreasing. They're moving at constant rates, and those rates are equal. The concentrations are constant. That would make the answer 3. Uh, 28 and 30 are the only ones that ask about the shifting. I'm probably going to find some or put some in a review pack for the test on this topic, which is going to be coming up. I'm probably going to, have that test for like Tuesday next week. But you'll see that when it comes. I'll do it on Castle Learning like I did the previous one. But 28 is a shifting question. It says, as the concentration of HCl decreases. So I'm taking away HCl. If we look back to this, right, it was the first one that I have here. Increase in one formula, we move away. If we decrease it, we got to come back. So this question is actually a shift left. In shifting to the left, the rate of the forward reaction is less. The reverse reaction increases, the forward reaction decreases. 28 is 1. If you have questions on any of these, and I'm assuming probably 28, 29, and 30 would be the ones that you have questions on, post. I'm still going back and reading the comment blog there. Please go ahead, post your questions. I'll make that my opening to the next video, of course. 29, given the reaction representing 2 SO2s and O2 gives 2 SO3 in equilibrium with 2 SO3 plus heat, which change will shift the equilibrium to the right, adding more O2. Increase in one formula, move away. So if I increase the O2, since it's on the left, it'll push it to the right. So number 29 is 1. 30, rule for pressure. It's a less usual case for the question, but rule for pressure. Increase in pressure, go to the side with less gases. What we have to do is use the coefficient moles to tell us how much gas is on each side. That's where this question is kind of unique. It says H2 gas. There's a 1 there. Remember the understood 1 if it's not written. Cl2 gas. Those are 2 gases on the left. There's 1 H2 gas, 1 Cl2 gas. On the right, we have 2 HCl's, both gases. 2 gases on the left, 2 gases on the right. There will be no shift of equilibrium with a change in pressure on this. Therefore, the answer is 3. It's going to remain the same. So those are the questions through 30. Entropy, enthalpy. Next section. We've already discussed enthalpy. That's the delta H. We're going to talk about these in regards to spontaneity of reactions. First little section there where it says enthalpy. There is a tendency in nature to change to a lower state of energy. A rock will fall down a hill. A rock will not fall up a hill. The spontaneous direction of change with regard to energy is downward. Therefore, exothermic reactions move to a lower state of energy because some of the energy contained in the reactions is released. The products have less potential energy than do the reactants. That whole little box, that whole little section, that first paragraph, box it. That is preferred by the universe. And then also write delta H negative. We're going to talk about changes in enthalpy and entropy and what's preferred. For enthalpy, delta H negative is the preferred case. That's all you need to know on that. The next slide talks about entropy. Entropy is S, and I don't know why. Entropy is S. Entropy is given the symbol S. It stands for the chaotic state or the randomness of a particular system. The entropy of the universe must increase as a whole during any spontaneous change. Excuse me. So if we look at the little checkerboard setups, figure 810, you see the first one is organized, Very neat. All the reds on one side, blacks on the other, every other one in each row and column, very organized. Then the game begins. One moved, entropy is now higher. Second or third move, entropy is higher as the pieces move around the board. You're increasing the randomness of the system. Systems that move to greater disorder, greater chaos are preferred in the universe. So that means the S, the entropy, would increase. Since any delta value is always final minus initial, like even delta T, like MC delta T, it's final minus initial. We never did that. We just did the absolute value of the change in temperature, but it's always final minus initial. So it's going to be S of the products minus S of the reactants. If it's becoming more random, entropy is higher on the product side. That's going to be delta S positive. Okay. So maybe you could, just like you wrote next to the enthalpy area box, what I think you should do is box off this little section on entropy, then write delta S positive is preferred by the universe. All right. Delta S positive is good. Delta S positive creates a spontaneous reaction. Therefore, what are the conditions that lead to a spontaneous reaction? I'll write that down. Spontaneous is delta H negative, delta S positive. If you have two values like this, if the H is negative and the S is positive, if it's an exothermic reaction that's increasing the disorder of the universe, that's a reaction that's going to proceed without help from us. A rock will fall down a hill for that reason. The rock can still go back up the hill, but I'm going to have to physically do work. I'm going to have to pick it up and carry it up the hill. It's not the spontaneous direction of change. The discharge of a battery is spontaneous. You can recharge that battery, though. That's not spontaneous. The non-spontaneous cases, the reactions that will never occur under any condition, would be H positive and S negative. Right? I've talked a little bit about entropy. Let me give you the conditions that would allow us to indicate that a reaction is increasing in entropy. I'd like you to think about this. If you think about our three states of matter, solids, liquids, and gases, which of the three states of matter do you think has higher entropy? A solid, a liquid, or a gas? If you thought gas, you were right. Gases have more random possibilities. They're constantly moving, spreading out throughout the universe. Gases have the highest amount of entropy. If we can move down to the bottom of this section, just above where it says review questions, the first statement there is on the states of matter. You can put a little star, box it, or underline it, whatever you'd like to do. The solid phase has the least entropy. The liquid phase has entropy, and which is less than the gas phase. Gases have the most entropy. Generally, the side of the equation with the greater number of molecules has the greater entropy. But if those molecules are gases, it's the most. And again, you're going back and adding up the coefficients of the equation. Usually number one is the one that they talk to you about. Also temperature, it's really not mentioned here, but higher temperatures have higher entropy. Right? Let's look at the review questions on the entropy section. I'm actually going to do them with you now. They're not terribly difficult. And I'd like to, at this point in time, just discuss with you briefly the equilibrium expression. After I finish this lesson, I am going to upload some questions for you. So, look for them, probably, 15 to 20 minutes after I have this posted. I had given them as a quiz in the past. It's a part 2 quiz. It's like 23, 24 questions. I'd like you to do those. I'll review those tomorrow. This is actually, I'm going to finish content on this topic today. I don't know. I'm going to figure out what's best to do as a strategy for you guys over the next couple of days, because I'd like to assign the test on Tuesday of next week. This way you have both Tuesday and Wednesday to attend to it. But let me get on task here with running into these questions. All right. Number 31. Which change in a sample of water is accompanied by the greatest increase in entropy? If you look at question choice 1, right, we have no Note a change in temperature is going from 100 to 200, and more importantly, it's going from a liquid to a gas. Okay. Uh, Question two also has that same temperature choice two. Sorry, choice two has that same temperature change, but it's going from a gas to a gas. So you're getting the biggest increase in entropy when you change the state of matter. Okay. Uh, Number 32, and gases have the most. When you go from a liquid to a gas, you increase your state of entropy more than any other change. Number 32, what occurs when a sample of carbon dioxide changes to carbon dioxide in the gaseous form? The gas has greater entropy and less order. So entropy is increased. So that's choice one. Number 33, we have a neat, nice, organized mass of argon on the left and neon on the right, and a valve between them. When you open the valve, they're going to mix. That increases disorder, so entropy will too increase. Number 34, which series of physical changes represents entropy increasing during each change? Choice 4, solid to a liquid to a gas. Gases have the most entropy, solids have the least. Number 35, in terms of entropy change and energy change, enthalpy is energy, right? Systems in nature tend to undergo changes to higher entropy and lower energy. That's 2. That's this condition, which I have written out right there on the board. 35, consider the following equation. Which will occur if the temperature of the system increases? Okay. If you increase the temperature, right, it's going to move away from the heat. This gets back to Le Chatelier's principle, which is part of the last topic. It's going to drive this reaction to the right. You're going to get more gas. And common sense, that should actually, be understood. If you have water and you heat the water is going to evaporate faster, or the water might even boil and vaporize. Okay? So increase in temperature, move away to the heat. It's going to move to the gas side, right? Favoring the endothermic process. High temperatures favor endothermic. Okay, so what will occur if the system is increased? The average kinetic energy of the system, that's going to increase, right? The entropy of the system will increase. That's the answer, probably. The number of moles of H2O gas, those are going to increase, not decrease. And the number of moles of H2O liquid, that will decrease, right? In shifting to the right, everything on the left is less, everything on the right is more. So H2O gas will increase. Having more gas means more entropy. Number 37, as NaCl dissolves according to the equation, the entropy of the system, NaCl is a solid, low entropy. NaAQ plus ClAQ, those are in the liquid state, right, dissolved into the water. We're taking a pure substance, making a mixture of substances. In the liquid state, entropy will increase, choice 2. And number 38, which change will result in an increase in entropy? Choice 2, solid to liquid would. And number 39, a reaction must be spontaneous if it is exothermic with an increase in entropy. Choice 3. All right. The last thing here is the equilibrium expression, or sometimes referred to as the mass action expression. I don't even know if we have any questions on that. I don't think there is. I don't know if they appear on the regions anymore. I'm not 100% sure on that. This is an equilibrium expression, so I just haven't seen too many of them made over the past few years. I am going to discuss it with you because it's in the book. I'm probably going to put like 1 or 2 maybe into the review pack, but I don't think this book has any questions on it, which is odd in that they have a description of it, but no questions. But it is the mass action expression. It's the product of the products over product of the reactants. So products go on top, reactants on the bottom. It creates an equilibrium constant. This constant allows us to predict how effective the reaction is. Will it go 100% over the products, although no reactions really go 100% over the products? Or is it an ineffective reaction where only a few products would be made? Let me just give you a very hypothetical one with A's and B's. All right. 3 moles of A plus 2 moles of B yield 3 moles of C. All right. So 3 of A plus 2 of B will make 3 of C. This is our hypothetical reaction. We're going to use the mass action expression. K is equal to products. This is our product. So we're getting 3 C's. So it's C, C, C. It's product of the products. So it's C times C times C, which, if we simplify it, this 3 means how many C's there are. If you multiply C 3 times, it's actually C cubed. So it's going to be C concentration of to the 3rd power, right? You put it in brackets, it means concentration, over A also to the 3rd power, and B to the 2nd power. That's the whole thing. It's actually pretty easy. All right. So if we look at the sample problem, which is all there is on this, given this is the Haber reaction, N2 plus 3H2 yields 2NH3 for the production of ammonia, plus heat. Heat doesn't go into the equation. It's just the concentration of the products and reactants. Notice when we go underneath, okay, it says place products over reactants, put the brackets in, and then take the coefficients, make them the exponents. We have an expression of equilibrium, NH3 squared over the concentration of H2 squared times the concentration of N2. That's it. Right? I'll be posting in a little while. I have some questions. They're part 2s, they're writtens. I'm working on the assumption that at some point in time we will be back in the building. With the latest thing with the president saying it's not going to be until we're going to be in quarantine until April 30th. Having heard that, the initial thought that we might be back by like the 20th, that's probably gone. They're probably going to keep us out till May 1st. I don't know. I would like to be back after the April break, but who knows what's possible. We just got to wait and see. So check back in a little while. I'm going to post those 20 whatever part 2 questions. This way, you can continue practicing those for your Regents exam, which hopefully will still be in June this year. We'll see. I don't know if, we're going to be out that long. I don't know about you guys. I think I'd rather be in the building. Anyhow, take it easy. Have a good day.